Hello everyone, I'm Changwei Zhou. Today I'm going to talk about how to protect return addresses on the core stack. This is a joint work with my supervisor, Professor Jinlin Xie. The new technique we provide is a shadow stack with microsecond-level runtime rerandomization. The term burn after reading in this title means that our runtime rerandomization is very fast, such that it can be done frequently to invalidate the disclosed information. First of all, we give a simple example to show how a buffer overflow vulnerability can be exploited to hijack the control flow. The get function called at line 3 reads input from the user, but it does not check whether the buffer at line 2 is large enough. A malicious user can provide more data than the buffer can support, such that the return address saved on the core stack will be modified. So when the function returns, the control flow will be hijacked. By the way, there is also a format string vulnerability at line 4, which can lead to information disclosure. There are several existing solutions for protecting return addresses, including code randomization, control flow integrity, and shadow stack. The shadow stack technique hides the return addresses in a hidden stack. It relies on hiding the location of the shadow stack, so it's vulnerable to information disclosure. As shown in this slide, the number of information disclosure vulnerabilities reported on the CVE website has risen quickly in recent years. There are some challenges we must face in runtime rerandomization. First, runtime code pointer checking is expensive. The state-of-art runtime rerandomization solution, runtime ASLR, which is published on NDSS 16, spends several seconds to conduct a round of rerandomization. Secondly, code pointer tracking is difficult. Although a low false positive has been achieved, it's hard to avoid. Third, to mitigate information disclosure, such as a format string vulnerability, runtime rerandomization should be conducted as frequently as possible. That is, it should be very fast. In this slide, we give the motivations of our research. First, we want to provide a microsecond-level runtime rerandomization mechanism for protecting return addresses on the core stack. Second, we observed that by adding one level of indirection, we can re-randomize the return IDs rather than remapping code sections. In this way, we do not need to do the time-consuming code pointer checking anymore. As a nice side effect, we also obtain an ability to catch the potential attack instantly. Third, our technique can be conducted frequently at any time to make the leaked return IDs invalid, that is, burn after reading. Our prototype is named as Bala. We have implemented Bala in the LLVM compiler tool chain. Fundamentally, Bala is an assembly instrumentator. For each return address, it has a corresponding return ID. When a return address is pushed on the core stack, we also store its corresponding return ID on the Bala stack. At runtime, we can generate a random value and add it to each return ID on the Bala stack. In this way, all these return IDs on the Bala stack are re-randomized. As shown in this slide, we can fork the input or output functions such that a runtime rerandomization will be triggered when these functions are called. Here is an example to explain a runtime rerandomization. The burn after reading at T3 makes the gadget ID 204. The attacker got at T2 still. That is invalid, such that the attacker cannot successfully hijack the control flow to the ROP gadget he needs. It's important to note that we do not need to reorder or hide our mapping table during runtime rerandomization. This design makes it extremely fast. In this slide, we give an example to explain how to instrument a call instruction and its corresponding return instruction. At lines 12 to 15, we randomize the return ID and save it on the bala stack. When the function returns, we retrieve its return ID by undoing the re-randomization as shown at lines 19 to 23. The instrumented data section is shown in this slide. At line 40, the render value, which is an 8-byte value, is stored in a 4 kilobyte page, such that the entire page can be set as read-only after each round of runtime randomization. Our evaluation demonstrates the efficiency and effectiveness of BALA in protecting return addresses. BALA shows comparable instrumentation overheads as the shadow stack, but at the cost of generating a little larger binaries on average. The runtime rerandomization overheads and the different core stack depths are listed in this table. In general, the time taken by our rerandomization is linearly proportional to the depth of the core stack. And this is the comparison between BALA and the runtime ASLR. In this slide, we give the statistics for the 19 C or C++ spec benchmarks. More details can be seen in our paper. By exploiting the format string vulnerability at line 4, we give a proof of concept attack to show the effectiveness of BALA. In fact, BALA is a 3-in-1 solution, which naturally combines shadow stack, control flow integrity, and runtime rerandomization together. We have also open sourced our prototype. In a word, we provide a microsecond-level runtime rerandomization technique for protecting return addresses. That's all. Thank you very much. Any question?